Hello everyone and welcome to this Construct 3 tutorial where you will learn how to make a match 3 game in Construct 3. As always, please like and subscribe, and you can find a link to the Sira store with a full template where you can download the template in the comment section. Let me just show you the finished project first. This is a menu now with 4 buttons corresponding to 4 levels. The gray buttons are locked levels and the green button here is an unlocked level. We just click the unlocked level and then we see some jewels popping up in different colors. And whenever we have a match of 3 or more jewels, they explode. We can just change jewels exchange place, and like any normal jewel match 3 game, like that. At the top left you can see the number of moves you have left. Here you see some targets. We need to get 2 more of those green jewels and 6 more of those blue jewels. Our score is currently 590. Let's get some more blue jewels here. Okay, and now they've all reset to 0. And then we have congratulations. If you now go to the main menu, you see there's an extra level unlocked. Okay, let me just go through the game and let me show you how that works. So we have a number of layouts, a menu, the game, and then a layout with some objects that are spawned inside the game. And we have a few event sheets. Here are the different object types, neatly categorized in a number of folders. And then there's 2 families. Now let's start with this jewel. So the menu contains a number of buttons, each corresponding to a level. A button has an instance variable called level. You see this? A level, which corresponds to the level for each button. They can also have an effect grayscale in order to give it locked levels a grayscale effect. This is one here with intensity 100. So you're free to create extra buttons for extra levels if you wish. It's very simple. If you go look at the event sheet, which is linked to it. So the different levels of the game are not hard-coded. It means that there is no layout for a single level. Instead, the levels are configured using a JSON file. At startup of the menu, the JSON file is read using the Ajax plugin. You can see that here. Here we use the asynchronous functionality of Construct 3 to wait for the project file to load into memory, and once that's done, the JSON file is read into the levels object. That's what we do here. And next here we use the local storage plugin to check the unlocked levels variable has been saved. The result is either the onSettings exists or on settings missing events that are being fired. So we check here for the unlocked level exists, and here at the bottom you can see when on local storage fires the exists event for unlocked level, means that it already exists and we can get the item. So it can again here this is an asynchronous function, so it used to wait for the item information, and then the local storage item value is used to set the unlocked level variable, and then the buttons are refreshed. Likewise, if the unlocked level item does not exist, then this event will be fired. We set it to 0 and we save it immediately. And we refresh the buttons as well. So this is the refresh buttons function. We activate the grayscale effect for levels that haven't been unlocked yet, like this, and we disable it for levels that have been unlocked. Finally, here in this event sheet, you can just see that when the level button has been clicked, then we check the instance variable level towards the unlocked level variable we picked up from the local storage plugin, and we set the level variable so we can check it in the game event sheet. It's used to pass the level through to the game event sheet, and then we go to the game layout. That's it. Now let's have a further look at the objects layout. The layout contains all of the object types that can be spawned during the game, and includes 7 different jewels, the particle effect that comes along with the explosion of a jewel, and the power up and the particle effect for the power up. All jewels are included in the jewels family because they share a common behavior. You can see it here. The cross has been added in here as well because it needs to have like another jewel. It needs to behave like another jewel. Furthermore, there's an extra family for power-ups where the cross power-up has also been added in it. It serves a different purpose and can be used when you decide you want to have more different power-ups to the game. The jewels family has a number of instance variables. First and foremost, there's a row and a column coordinate. These coordinates denote the exact place in the grid where the jewel is located at the moment. They are used to determine which jewels is beside it, above it, and below it. Furthermore, there are also instance variables for the original X and Y values that are kept when the jewel is being dragged by the user. And lastly, there is the jewel type, being the color of the jewel or the name of the power-up. The jewel family also has 3 behaviors attached to it. The move to behavior takes care of the movement of the jewels, basically some basic settings, but important to note here is the maximum speed that has been augmented quite a bit. Next to that, the tween behavior is used to fade in the opacity of the jewels, and last but not least, the drag and drop behavior lets the user drag the jewel around. The power-up is in the second family, and in addition to it, it gets the sign behavior to make the scale go up and down in a sine wave when the power-up is on the screen. When the power-up is on the screen, some particles are emitting from it. The particle effects have been grouped into the power-up container. They have some basic settings, and most important, the spray cone has been set to 360 degrees, and it spreads all the way, and the type has been set to continuous spray. The image itself is the same image as the power up. Finally, there's the explode particle effect that is used whenever the jewel explodes. It has been given a select color effect that can be used to change the color of the particles at runtime. The advantage here is that you don't need a particle effect for every corresponding jewel. The image of the particle effect is a smoke image that I got from the Candy asset bundle. When you can find it at itch.io, just like all the other assets you can find in the game, such as the font and all the other sprites. It had also a spray cone of 360 degrees, but this one is a one-shot type. Finally, let's go to our game layout. Let's expand that a bit. So the game layout consists out of a number of layers. The HUD layer contains all of the items of the top layer. At the top of the layer, you see the number of moves the player has left, up to 3 possible targets, and the current score. Dialog layer contains all of the objects concerning the game over dialog. The dialog is shown by either showing or hiding the layer. The debug layer is only there to keep a number of objects that help debugging the application. The explosions layer is empty, but will hold the explosions particles created by the jewel when the jewel is exploded. The jewels itself will be spawned at the jewels layer. The background layer only contains the background. The grid layer is the layer where all the placeholders reside. Placeholders are the gray boxes that are hidden from the user at runtime. The only purpose they serve is to keep track of the exact x and y coordinates Joule has to move it to a certain row and column. For that reason, all placeholders hold two instance variables called row and column. Using the row and column, the correct placeholder can be picked and the x and y coordinates can be deducted. Just above the placeholders, red squares are visible. These are spawn points. They are also hidden from the user at runtime, and they are references as to where a new Joule has to spawn. In the HUD, 3 references can be found to a target. They all have the same sprite and a corresponding text. However, these are 3 times the same object. The way the distinction can be made between the 3 is using an instant variable called target ID. There's no sprite target for every target. No target sprite for every target. Instead, every target is included as a frame in the animation in the sprite. The frame is selected at runtime. So now let's go and look at the game event sheet. The game event sheet contains a number of variables that are used throughout the logic, and also includes a separate event sheet called constants that contain a number of constant values that are used inside the game. So let's go over the different functionalities. The functionalities have been grouped into different groups. Let's start off with the base functions. So we start with on every tick. On every tick, we constantly update the moves and the score actually. And we also constantly update the targets. So we pick the different targets using their target ID, and we update the target countdown here. The cross power up, when it's created, we also pick all the power ups that are currently on the screen, and we set the scale to 0.8 minus the sign value. This is a slight increase and decrease in the scale whenever the power up is on the screen. And when power up is created, we also pin the particles to the cross power up using the pin behavior. Then there's a vast number of functions actually. I'm really a fan of functions because they really get your code together and you can give them a nice description, and if the logic needs to be executed more than once, you can just call the function. So there are quite some functions in this project. First, there is the move Joule, and this function will move a Joule from its current position to a new position, denoted by the dest row and dest column coordinates. We pick the Joule by its ID and we pick the placeholder by its column and row coordinates. Then we set the speed to move it with a certain constant speed. And we add a number to the moving path semaphore to check the on move to. The reasoning behind this is that the move Joule function will be called simultaneously for multiple Joules. The move to arrived event will therefore be called for every Joule, while this only needs to be done for the very last Joule when it falls into place. That's why the counter increases every time a Joule gets moving and will be decreased in the on move to arrived event. We'll see that a bit later. Actually, move the Joule using the move to behavior here. Here the move the position. Here the move to position option is used. We also move there in directly and not using any waypoints of some sort. And then we set the new coordinates of the Joule. Cool. This placeholder field is actually a helper function. This function will tell the caller of the function if the certain placeholder currently contains a Joule or not. The default return value is 0, which is only returned if the picking operation is not successful. When construct 3 is successful in picking a Joule, the result will be 1. And then there's the on move to arrived event, and this event is one of the most important events in the game. It's fired every time a jewel has moved into place. There are, however, some occasions where it cannot execute its code. The first thing is when dragging has been disabled. This is usually the case when jewels are exploding and the grid is being repopulated with new jewels. When dragging is enabled, however, we still need to check if there are currently not jewels falling, for this event, for which this event will also be called. To avoid this event can be called too many times. Moving part variables is used to detect the number of jewels that are still moving. Only when there are none moving, the code should continue. So once all jewels have fallen, so moving parts equals 0, we check the grid if there are jewels eligible to explode. The check grid will return a non-zero number whenever it detects that. At the moment, there are jewels on the grid that can be exploded. If so, they can be exploded by calling the check grid and explode function. So if check grid bigger than 0, explode, check grid and explode. Else, no jewels are eligible to explode. Now we can start checking some conditions to see if the game should end or not. Check if the game succeeds, targets have been met. When all targets become 0, that game has succeeded. We show the dialog with parameter 1 for success. Else, when we see the targets have not been met yet, we check if there are any moves left. If there are no more moves left, the game can quit with success. You can show the game over dialog actually. And finally, we can enable the dragging so this event can execute its code again. So the code above is executed regardless if the jewels need to explode because of the fact that the grid is refilling or because of the user that has dragged the jewel around. However, if the check after swap flag equals 1, it means the user has swapped a jewel. At that time, we subtract 1 from the moves left variable, so that's the number of moves the user have left in the game, and we reset the flag check after swap. If the jewels we are dragging is a power up, we can check the get jewel for coordinate here, which will return me the type, the jewel type for coordinate, which will return the type of the jewel at a given row and column position. If it is a cross power up, then we handle the power up. For the dragged row and the dragged column, which is the row and the column of the jewel being dragged. When a jewel is dragged around, the jewel, when it dragged, is going to drag towards another jewel. The jewel that the drag is going towards is moving in the opposite direction. This is called the counterpart jewel. So we also need to check if the counterpart is a jewel or not. So if the get jewel type for coordinates of the counterpart equals a cross power up, then we can handle the power up as well, but now with row coordinates of the counterpart, so the row and the column of the counterpart. So else the jewel is not that's being dragged around is not a power up, and we can check if the drag yields a number of jewels that can be exploded. So the check grid here again will select you or would return you a number which is non-zero if there are jewels to be exploded on the grid. If that's not the case, the user did make a valid choice, so the drag jewel and its counterpart needs to be swapped again to their original place. And finally, if there are no more jewels left after the drag operation, the user needs to be presented with the game over dialog. So moves left equals 0, game over. Then let's have a look at the init behavior. On start of layout, we will execute some code. The choice of the colors of the jewels is done using the advanced random plugin using a probability table. Here we create a probability table and we call it jewels. And the probability table can be filled with entries, where the weight of the entries is determined by the level that was loaded and the entries in the JSON file. We also move set the moves left according to the JSON file, and we initialize the score. We also initialize the targets from the JSON file, both the type of the target and the countdown level of the target. So there are 3 target sprites on the game layout. However, there are no 3 objects, object type. To keep them apart, the target ID instance variable can be used. So we pick the target sprite by evaluating the target ID here, and all the jewels are frames in the animation, so we set that to stop the animation so the frame can be selected manually. Setting the frame itself can be done using this complex expression. Finally, we have to make sure to hide the dialog before we start the game, and we can start by filling the grid again. Spawning a jewel. Jewels start on the screen with opacity of 0. As an animation, we tween the opacity to 100 using the tween behavior. This is done when a jewel overlaps a spawning point. And then there are a number of helper functions to assist in spawning a button. So the refill column function refills a certain column, and that happens in 2 phases. First, we check if there are empty holes in the column. All of the empty holes are filled using jewels that are already on the grid in the same column. However, those jewels, whenever the jewels fall into place, new jewels are spawned in the second phase to fill the open places on the top of the columns. The algorithm starts from the bottom, from 0 to number of rows -1, and we set a flag. We use the isPlaceholder filled function to check if there is an empty hole, and then we loop through the holes and find a replacement. Until a replacement is found. We continue until a replacement is found, and now we can assign the new row and mark as our search is done. Now that every jewel has got its new coordinates, we can move them into place. We select the jewels, and for each jewel we call the move jewel function. And finally, we spawn new jewels for the holes that have been created at the top of that function. We use the spawn column function for that. That's the next function I will describe. So this function just fills all of empty available holes in the column. We just loop through the rows, and if the placeholder is empty, we spawn a jewel for that placeholder. We call spawn jewel for placeholder. And that's this next function. So this function will effectively create the jewel and move it to the correct coordinates. First, we pick the spawn point for the designated column, and we use the advanced random weighted functionality to get a value from the probability table. We create an object of that type at the spawn point. So next we pick the last created jewel. We default the row and column coordinates. They will be set in to its final coordinate by the move jewel function. We set the jewel type, and then we set the starting point of the move to a distance above the spawn equal to the distance to the destination row, so the jewels fall down nicely in the correct order and they don't overlap when they are falling. We start with the opacity 0. Once they have passed the spawn point, the opacity will be tweened to 100. We make sure that the user can't drag the jewel when falling down. And finally, we move it into place using the move jewel function. And then lastly, there is the function fill grid. This function fills the entire grid with jewels. So we loop through all the columns, and we call the refill column function I already explained. So then there's dragging. There are 3 events: on drag start, on drag drop, and on drag dragging. So on drag start, we set the drag state so we can check it if we are already dragging. The drag state will tell us how we are dragging during the operation. It can be dragging to denote that the dragging operation has started, but we don't know yet if we are dragging horizontally or vertically. So we just start off with dragging. When starting our drag operation, we also need to keep track of the original coordinates of the jewel, so we can move them back into place when we need that. That's why we initialize the original coordinates. We move the drag jewel to the top of the layer, so it's always passing above its counterpart. And finally, we set the variables of the dragged row important, so we can check in other functions which jewel is being dragged. The onDrag drop. We will reset the jewel to the exact positions of where it should be in respect to the placeholder. Sometimes due to synchronization issues between drag drop and dragging events, dropping a jewel might not be exactly landing on the X and Y coordinates of the placeholder. So if a user has started dragging and he has dragged the jewel far enough, we need to swap the jewels. The drag range variable is set when the user is dragging and denotes how far the user has dragged the jewel. It compares to a tolerance. If the drag operation is not dragging the jewel far enough, for example when just clicking the jewel and not dragging it, nothing needs to happen. Else, we need it to be swapped. Finally, we go and reset the dragging range and reset the drag state, so the next drag will start from scratch. So the drag drop is dragging. This event primarily takes care of the fact that the jewels cannot be dragged somewhere else on the screen than the area between the drag jewels and the counterpart jewel. So first we determine how the jewel is being dragged, horizontally or vertically. So here the jewel is being dragged within the tolerance zone, so it's not vertical nor horizontal. Dragging away from the horizontal tolerance but within the vertical tolerance means that the drag state is horizontal. And dragging away from the vertical tolerance but within the horizontal tolerance means that the drag state is vertical. Depending on dragging horizontally or vertically, we use the original coordinates to determine the distance the jewel has been traveling depending on its original position, and how the counterpart and move the counterpart in exactly the opposite direction with the same amount. If it is the first column, the user cannot drag it outside the boundaries of the grid, and the same thing applies for the rightmost column. In all other cases, the jewels can be confined within the x coordinates of the preceding and the next placeholder. We use the clamp function for that. The same thing applies when dragging vertically. So in all other cases, the jewel should stay in its original position and can be reset to that exact position. Furthermore, the counterpart jewel needs to be put back in its place as well. We can call the reset jewel function for that. So then we set the drop x and drop y variables to make sure the jewel ends up exactly at the placeholder, bypassing possible synchronization issues between the drag drop and the dragging events. So then there's a function called move counterpart. This function will effectively move the counterpart jewel in the opposite direction of the jewel that's being dragged. We first need to determine which jewel is the counterpart and fill the counterpart column and row variables. If you're dragging horizontally to the right, we set the counterpart column to the dragged column +1 and the counterpart row exactly the same as the dragged row. So if we're dragging horizontally to the left, we pick the column to the left. So if the drag state is horizontal, we can set the x coordinate and make sure it stays nicely in range. This can be done using the drag range variable, which is set in the dragging operation. So then we check if we're dragging vertically down or vertically up, and we set the y coordinate and make sure it stays nicely in range, equivalent to what we did in the horizontal logic. So this function, we already called it to initialize the original coordinates. So we go through every jewel and we set the oreg x and original y to the x and y coordinates of the jewel. The reset jewel, this function will move a jewel with the selected row and column coordinates into place using the move to behavior that's it. The swap dragged function. This function will swap the jewel that's being dragged with its counterpart. It uses the four variables dragged row and dragged column and counterpart row and counterpart column. So we first pick the dragged jewel and the placeholder for the counterpart. We move the jewels in its place and remember the UID so we can use it here later. And now we pick the reverse and remove the reverse and remember the UID as well. Using the remembered UIDs, we can assign the new coordinates to the joules. That's it. So then there's some help functions just to disable the drag drop behavior of joules and to enable them again. So the next section is to be able to check check the grid if there are joules eligible for explosion. Check grid and explode is a little helper function that just checks the grid and explodes them, and after that it fills the grid again. The check grid function will return a non-zero number if there are joules to explode. Then we make them explode. Explode all as an asynchronous function, so we can wait until all explosions are done before we fill the grid again. Get joule for coordinate is yet another helper function that will simply return the joule type of a joule at a certain coordinate. We do default it to a certain joule type, which is not a joule type, none in this case, and only if we pick the joule, then the return value will be set to the correct joule type. And then there's the function that checks a certain coordinate for eligible explosions. This function evaluates a certain joule at a certain coordinate and checks if the joules around it horizontally and vertically are of the same type, and only if it matches 3 or more of the same type, the temp dictionary will be filled. First we check horizontally on both sides and then vertically also on both sides. We have to initialize some variables, and we have to reset the temporary dictionary that will be used by the check grid function to determine if this coordinate has entries marked as selected. So first we check horizontally to the right, and we default some values. So now we look to the right until there is no match. This is done using a counter that is augmented until no match has been found. At that time, the stop flag is also set. If it matches the current value, add it to the loop dictionary. We pick the joule, and if it's not already in the loop dictionary, we can add it to the loop dictionary, and we can add one to the horizontal counter. Else we can just stop looping, and we take the loop dictionary and each key goes into the horizontal dictionary. And then we add the counter to start again. Now we have to do the same using the left side. This is because the 3 or more in a row can be a combination of joules to the left and to the right. Therefore the same logic is done, and finally the horizontal dictionary is finalized. The horizontal counter will denote if there are 3 or more joules. So again we do the while loop, we add it to the loop dictionary, and only if the horizontal counter we set here is greater than or equal than 3, then we fill up the horizontal dictionary. Else, if the left and right don't yield 3 or more, they don't count, and we clear the dictionary. And then finally we add everything to the temp dictionary, which will be used in the fill grid function. And then we do the entire same thing for down and up. Finally, if we have some matches, we will add the joule that's being evaluated as well to the temp dictionary, so it can explode as well. So that's for check coordinate. This check coordinate is used here in check grid. So this function checks all joules in the grid using the check coordinate function. It fills a dictionary called the explode dictionary, and will return the number of keys in this dictionary. So we start by clearing the explode dictionary, which will be used to mark the items to explode. And we loop through the columns and through the rows to loop through every joule. So we also get the current type of the jewels using the get jewel type for coordinate function. If it's not a power up, we check the coordinates to fill the temp dictionary with all jewels that were matched. So this function check coordinate will fill the temp dictionary, and here we loop through it for each value in the temp dictionary. If the value of the current value is not already in the explode dictionary, we can add it to the explode dictionary. And so finally, we set return value to the number of entries in the explode dictionary, so expressions that call this function can check if there are any matches in the entire grid. So this section takes care of the explosion logic. There's an explode jewel function. This function explodes the jewels and takes care of the animation. We pick the jewel that is going to be exploded by its row and column, and we create an explosion particle on the correct place. We adjust the parameter to fit the color of the jewel. This is done using the 0 parameter of the set color effect. So the RGBX255 function denotes the color in red, green and blue values. We add something to the score and we take care of the targets. We set the countdown to countdown -0, but make sure that it does not go below 0. And then we finally get rid of the jewel. Here's where you can add some sound effects or something like that. Then the function explode all is an asynchronous function which will loop through the explode dictionary and will call the explode jewel for every jewel in the row, in the column and row combination. The game over dialog has a little function called a hide game over dialog. We hide the dialog by just hiding the layer, and we disable the logic so the code for the buttons doesn't get executed when the dialog is hidden and the buttons are inadvertently pressed. Show game over does the same thing but reversed. We have a parameter that the success denotes when the level has been completed. 1 is successful and 0 is not successful. We show the dialog by showing the layer, and we call disable dragging, and we activate the buttons on the dialog here again. So if success is 1, we set the title to congratulations. Else we set the title to game over, and if the level is equal to the unlocked level, so it's the last level that's being played, we also add 1 to the unlocked level and we set it immediately in the local storage. And in the power up section, we only have one function to handle the power up. So it will also fill the explosion dictionary, and the explode all function will loop through it and perform the explosion logic. Only if the type of the jewel being passed is actually a power up, of course. We pick the jewels by using the jewel coordinate given as a parameter, and we, for each of the jewels that are either in the row or either in the column, for each jewel we will use it or add it to the explosion dictionary. And if it's not empty, we will call explode all, wait for all explosions to continue, and we can fill the grid again. So this is the logic for the entire game. I will leave a link to the Sierra store in the description where you can pick up this entire template as I explained to you now. So as always, please like and subscribe to get more tutorials like this one.